Now we have seen a review of introduction to robotics. Let's now talk about a very important aspect of every machine, every device, and that is controlling it. And this course, of course, assumes that you already had a first course in control, or maybe even more. So let me go back to my station, and we're going to talk about control paradigms from the most celebrated control paradigm called PID, which on Earth to autonomous control paradigm on Mars. You all have seen this block diagram. This is a feedback control system. On the left you see a desired input, y of d. On the right you have an output y of t. The objective is to match the output to follow the input. If the input is a function of time like you see here, then this whole process, objective of this whole control system is what we call tracking. When you want to put, send a rocket to the space and place, let's say, a satellite in an orbit, you're doing a tracking control problem. Because that trajectory moving to the right orbit is the desired input, which the control engineers on Earth has already figured it out in the factory floor. It won't happen in the classroom. It happens in the industry. Okay. Could it be Lockheed Martin or Boeing or what have you? The difference between and if the input is constant, like the temperature of this room at any given instant of time, you want, your controller could be your air conditioner, or rather an actuator which turns on and off the air conditioner, which is the plant. Your air conditioner is the plant. In that case, when you have input and output both being constant, you're dealing with regulation. You're regulating a constant value, constant, like temperature. Or you, for example, want to temperature of the room is your output, your desired temperature, maybe 70 degrees Fahrenheit or 72 degrees room temperature, 26 degrees Celsius is your reference input. The difference is the error. We call it E of t. E of t is the signal which tells the controller of what to do with the plan in order to move toward your desired goal. Okay. And of course, no control system can go anywhere, no robot can go anywhere without sensing. You need sensing devices to measure the temperature, measure the depth of an image, measure all kinds of things like pressure, many other height, you name it. All of those physical quantities have to be measured by some kind of sensors. And we do have modular sensors in the lab where you can put different modules of sensors on top of each other. At any given level of the modularity, you can measure something different than the others. So the objective of this as a control system is to find a controller such that the limit of this error goes to in the long time in the future will become zero. That means you already reached the right orbit and you can now release the satellite and put it in that orbit. At that point, the error should be zero. Okay? And that is what we're talking about. And then, of course, when your air conditioner is on, your heater in the winter or cooler in the summer, it raises the temperature in the winter, becomes comfortable, it shuts down. Okay? You're familiar with all of that. So, multi-term controllers, so-called multi-term controllers, PI, PD, PID. P stands for proportional feedback. I is the integral feedback, and D is the derivative feedback. And you can see the equation down below here, the proportional plus integral plus derivative. P represents the error situation and penalizing error at the present time. So P stands for present. The error at this instant of time is being penalized because of Kp. The error in the past, accumulation of the error through this integration, accumulated error is going to be penalized by Ki, the second term. And as you can see, because of that integration operation, whatever the number of variables, what so-called state variables in the plant, this integral adds one to it. If you have only one input, if you have more than one input, you add so many variables to the plant. Becomes a bit more complicated because of that, but not too complicated. And of course, you have the derivative. Derivative control, the D part, looks in the future because it looks at the slope of the error, the way it's going down or going up. If the slope is positive, it's trying to penalize it, bring it down. Okay? And make it go down toward a zero value later on. So PID is a very powerful controller. And 90% of controllers in the world are PID type. Of course, if you don't worry about tracking, you can eliminate the integral part. PD is good to stabilize and to regulate any control system. And later on in this course, and with the help of our teaching assistant, you learn how to not only use toolboxes to do this, you can also learn how to do it in what we call fuzzy logic controller or intelligent controller, a toolbox for fuzzy logic controller. You can do that, and you can have a version of PID, which we call it fuzzy PID. Okay, so that you will have fuzzy if-then rules, expert rules for any component of the controller. Okay, and sometimes you can combine more than one rule together, and then you will have one expert rule to handle P and D together, for example. Optimal control is another branch of control system. This being a review of control system, you have a nonlinear differential equation for your plant. You have a sensing, which could be in general nonlinear, and you may have a constraint on your control signal. It has to be between minus and plus A, for example. The mission to Mars, the mission to Moon, which happened on June 19, 1969, before all of you were born, it was actually an optimal control like this. And the thrust on the moon lander had to switch 180 degrees from minus quantity maximum to plus maximum to be able to soft land on moon. So in this case, the control is finding a U such that it will satisfy the above conditions while minimizing a cost function like this. And that cost function could be many, many things to many different applications, depending on the particular application. It could be a combination of quadratic terms in state and control vectors, which is a measure of state variations, penalization, and or the energy consumption. You could even have a different architecture for this integrand for the time. It takes going from A to B. That's called minimum time, optimal control. Or you have fuel, minimum fuel. When you have deep space application, you have to worry about fuel. Okay, and to the success and to the glory of some of our dedicated
NASA scientists, they figured out how to send a rover on Mars and how to lengthen the life of the batteries on board from 3 months, which first one did 92 days. I remember it because I was involved a little bit on it. 92 days was the first mission. Second one was 4.5 years, because they figured out the problem. And basically, the solar panels get dusty on planet. The more dust goes on it, the less solar energy is going to be absorbed. So they found out a way to switch the polarity and use the gravity or whatever is left of gravity there to have all the dust go down. Then they bring it back and switch the polarity and becomes like a new battery. That's how they stay there for a long time. Here is how the moon lander landed. You have a linear continuous time system, you have a linear sensor, and you have the constraint on the control signal. This control signal can only take two values, either -A or +A. In between, it turns out to be non-optimal. So find the control U such that it would satisfy the above condition, these four equations, while minimizing the cost function 1/2 of the integral dt. What is this? This is nothing but time which goes from orbiter around what we call Columbia orbiter around Moon to the soft landing on Moon. So that was wanted to get down there in minimum time, where of course the dedicated engineers like Neil Armstrong was the first man who landed on Mars. He was actually in that moon lander with two others or one other. Optimal solution is -A + A, meaning that you come first to the maximum negative quantity on the thrust, somewhere in the middle, which is the switching point, which can be predicted through theory of optimal control what time it is in the middle, from initial time to final time. You switch full force into the positive thrust and you land on it. Now look at other options. Suppose you had only -A only. When you go -A, you come boom and you crash on the floor with a negative velocity. This is your velocity. You crash on the surface of the moon. Or you can actually go to +A only. If you go to +A, you're going to go like this. You go back, hopefully to Earth, but it's not going to happen. It's going to be lost in the deep space. So that is not good either. And the other alternative is you go to plus and then minus. You go to plus, which is going this way, and then minus brings you down, and you crash later on. So you have one lost spacecraft, two crashes, and one soft landing. 4 choices. Okay? And obviously, optimal control theory is programmed, and the modern control theory boosted a lot because of the Apollo project in the 1960s. Okay? In this country. There are a variety of other controllers that if you go on to graduate school or maybe even take as an elective before you get your bachelor's degree, it's called adaptive control. Adaptive control is a phenomenon which been promoted by both Americans and Western European control engineers from Sweden and other countries, and pioneers like Professor Carl Astrom from Sweden, and many others, of course, here in America. The idea is the following. All these control algorithms, which I should have mentioned it earlier, are based on a mathematical model of the planet. I repeat, the control algorithm is based on the mathematical model of the plan. That means you're bringing physical principles, Newton's law, thermodynamic law, energy conservation, etc., apply it to your plan, and you come up with a mathematical representation. Very often it could be a differential equation. Or if you go into discrete environment, it's a difference equation. Okay? And it may have some variety, it could have some time delays in it. It may have, nowadays with cyber physical systems, you may have communication-based delays in it, network delays, process delays, all kinds of things, which all contribute to instability of the system. Okay? The idea is the following. When you have a physical system, but for your design purpose, you're representing it by a mathematical model of it, as good as that model may be, it's not the real thing. So you put your controller, in this case, this controller I'm showing to you, this controller is based on the mathematical model of this plan, and you close the loop, and for most of the time you may be okay, be happy. And that's what you're going to be doing in the laboratory here for your experiment. You're going to do that. However, if you change the behavior of that plan, okay, if you have some, what I call unmodeled dynamics, okay, International Space Station, in the 80s, I had a graduate student who was modeling International Space Station. It is nothing short of an infinite dimensional system. But can we, as control engineers, design a controller for an infinite dimensional system? No way. So what do we have to do? We have a reduced model of the real system. If the model has 200 variables and you're hanging on to 25 of those, something has to let go of 175 modes of that system which are not represented in your model. You follow me? Therefore, in real application of that controller for that plan, some of those 175 modes may be excited and there is no way to compensate for it because it wasn't not part of the control design process. Okay? In the space industry, they call it a spillover problem. It spills over to something which cannot be handled. Coming to your rescue is adaptive control. Adaptive control, as you see, is additional block diagram here, which looks at the stability of this control system. Let's say on Lyapunov approaches. Lyapunov approaches, those of you undergraduates are not familiar, but the graduate students already know Lyapunov stability. Based on the Lyapunov function and Lyapunov stability, you can design an adaptation algorithm which controls your controller. Controls your controller. It changes its behavior in real time to keep up with the changes in the plan. This is what's called adaptive control. And we have a course on that in our department, which you can take. And later on, actually, you can even use an expert rule. You know, imagine that you are the expert for a system, and you have your control knobs in front of you, and then you see the plan is vibrating or it's not doing very well. You play with this KP and KI and KD or PID control. You change those variables. Okay? So what you do is a knowledge that can be used later. So we actually can mimic in fuzzy logic, fuzzy system point of view. We can mimic an expert like a control engineer and put fuzzy if-then rules here in place of this algorithm. And online in real time change the gains of the PID. If the error is low and change of error is high, then KP is equal to this. Simple as that. And this is coming from an expert operator, which may be retiring next month, but before he retires, we can take all his knowledge and put it into a chip. It is done. It's done for 20 years already. Okay? And that's how it works. Okay? Robust control is another area which one of my colleagues is expert on it. You have a linear control system which takes into account unmodeled dynamics by this additional matrix, dA, and give it a bound, the condition on it. And you want to find the control use such that it would satisfy this condition, minimizing one of the many possible cost functions involving different norms. L2 norm, L infinity, H2 or H infinity norm. These are the definitions of those norms. This is called robust controller. It has a beautiful theory. But to the best of my knowledge, it hasn't yet found its way to real world. Simply because a lot of times the architecture of the controller is more complicated than the plant itself. If you have a second order system, you may have a fifth order controller for it. Okay? And that means money, cost. Okay? Decentralized control, what is that? Decentralized control is the way that utility companies, power companies operate. You have a large scale system, and later on you will be given a website of downloading my books, some of my 11 textbooks in electronic format. All except 3 of them are downloadable, free. The other 3 are on Amazon.com, and they're not cheap. So we can give you a pre-publication copy, a rough draft of it. So imagine that here is the CPS energy here in San Antonio, but it is linked to New Mexico Power, or it may be linked to Mexican country of Mexico's grid. It may be connected to Oklahoma and so forth. So looking at this area of the country, you're talking about a large complex system. Okay. Now each of those electrical power plants have their own control to worry about. Controller 1 could be CPS, controller N could be PG&G in San Diego, or what have you. You may know that we have 3 electric grids in this country. We have Western grid, Eastern grid, and we have Texas. We used to be a country. So we have 3 grids, okay? And each of them are complex systems, okay? And all these different controllers are collaborating, working to make this large complex system reliable and stable, no blackouts, etc., things like that. Okay. So large scale power system is in fact a very important decentralized control application of the system. Hierarchy control goes in a different direction. Instead of decentralizing the control function, you are decomposing the whole system. This could be your chairman of the board. This could be division directors or division or vice presidents. This could be a management structure of a company. Okay? And all the way at the factory floor, you may have, workers and labor forces. Okay? So they're dividing groups into subsystems. Each subsystem will have its own subparts, and they report to the coordinator or subsystem, and all of them report together collectively. Then the subsystem, this coordinator, figures out the feasibility of your accumulated control paradigms or regimes. So, no, this is not good together. Because remember, you were one system together, we decomposed you. We lost some interaction among you. And you have to work in a way that will compensate for that loss of interaction. Okay. A good example of this also is if you have your what we call a state engineer's office. In many states, fortunately, we have a lot of rivers in this country. When the river goes from the top of your estate all the way down, goes into a body of open sea, everybody needs to have a right to that water. And the water which is extracted from the upper region has to let go, has to be at least what the second region wants. That is the coordination, okay, the connection, interconnection between these water resources system. I've got some publication and work in that framework of large-scale system. So you cannot just use up all the water and give nothing to the other one. So this approach is also, we call it hierarchical control, okay? Where the control is in a hierarchy, as you can see, okay? And this can be done on the robot. How? For example, if you have a swarm of robots, those members of the swarm is your subsystem. At the higher level, on maybe a ground station, or maybe your laptop, or maybe a cloud infrastructure, is picking up the sensing information from all of these robots, and the robot has some local control on their own feedbacks, but they also have a global control, a supervisory control, which comes from a higher up to control them as a group, moving them around like the bees or ants and other biological or other algorithms. Okay, so that's what's happening here. You can combine these different paradigms together. You can have hybrid control. You can, throughout the years, you have numerous hybrid approaches. You can have a decentralized and adaptive control. You could have adaptive and robust control. You could have robust and decentralized and so forth. And later on in this course, you learn how to combine artificial intelligence, AI, and let's say control theory, and apply it for a robot, okay? And then this becomes autonomous control. Now you know why we call autonomous control engineering lab, ACE, okay? So what is autonomous control? Maybe this is a time to stop, and then we'll take